Hi students, welcome to the science class. In last session, under the chapter of electricity, we discussed about the properties of the electricity and some of the laws of the electricity, that is Ohm's law, isn't it? So now in this session, we are going to start your one important lessons, very important lessons for your examination and also for your future studies, that is nothing but magnetic effect of electric current, isn't it? So the magnetic effect of electric current. In the headline there is a one word, that is magnet. Do you know already about the magnet? So then tell me, what is the mean by a magnet? What is a magnet? So magnet, what is magnet? Magnet, it is any material which attracts iron like material. Magnet, it is a material which attracts iron like materials. So magnet, it is a one type of material which attracts iron like material. Now I have one example here, that is one type of the magnet here. So in the magnet there are many types of the magnets are present. Now, the types of the magnets are bar magnet, just it is like that, a bar magnet, and horseshoe magnet, then circular magnet. There are types of the magnets are present here. Now I am having the piece of a circular magnet, isn't it? So what if the definition of the magnet, that is the what we are going to say, it is the magnet attracts iron like material. So it attracts iron like materials, as you know already. The magnet always attracts the iron like materials. Then what are the properties of the magnet here? So what are the properties of the magnet? Properties of the magnet. First property, when you are going to consider any magnet, it always has two poles. We have to remember, magnet always has two poles. Magnet always has two poles, that is north pole and south pole. North pole and south pole. Here in a circular magnet, that is one side it is a north and another one side it is a south. So every magnet always has two poles, that is a north pole and another one is a south pole. So when you are going to consider a magnet, so how much distance it attracts a magnet? Or the distance between the magnet, that is the displacement, that is the distance between the magnet which attracts the iron material. That distance, it is nothing but a magnetic field. So that magnetic field, it is due to the magnetic field lines, isn't it? So consider here, if you are going to consider a bar magnet, that is, it has two poles, north and south, isn't it? So when you are going to consider a bar magnet, north and south, the magnetic field, it is around this, isn't it? But it is due to the magnetic field lines which are present around the magnet. But how they are present? So the magnetic field lines around a bar magnet, they are starts at the outside. The magnetic field lines are started with the north end and ends with the south end. Starts with the north end and ends with the south end. And inside the magnet, The magnetic field lines are starts with the south end and ends with the north end. This is under one property here. The magnetic field lines are closed curves. The magnet attracts the materials if the iron materials comes in the place at which the magnetic field lines are present. Have you got understood? In this covered area, if any iron materials will comes, then only it attracts. That is nothing but it's a magnetic field. Have you got understood? It is due to the field lines, and these field lines are always curved, closed curves. That is one of the property of the magnet here. Magnetic field lines are closed curves, and magnetic field lines outside the magnet starts with north pole and ends in south pole. These magnetic field lines are all starts with the north pole and ends in a south pole. So inside the magnet what happens? These are the outside the magnetic field lines, but inside the magnetic field, the field lines inside the magnetic field lines inside a magnet starts with south pole. See here, this is inside the magnet. These magnetic lines starts with the south pole and ends in the north pole. So this is another one property of the magnet, that is the magnetic field lines inside the magnet that starts with the south pole and ends in the north pole. If you are going to divide a magnet any pieces, it always has the two poles and it always has the magnetic field lines, and in every piece of the magnet has the magnetic field lines, and the magnetic field lines outside the magnet that will be starts with the north pole and ends in the south pole, and inside the magnet that the magnetic field lines are starts with the south pole and ends in the north pole. You have to remember. So when any iron material attracts only when they are get contact with this covered magnetic field line covered area. If iron comes contact with this magnetic field line area, then only the magnet will be attracts that iron material, isn't it? That is known as the magnetic strength, that is magnetic field lines when they are comes under. So under one property here, when you are going to left a magnet freely, it always stands in a north-south direction. When you are going to place a bar magnet, I am not consider here a bar magnet. If any magnet you are going to place, when you are going to place a bar magnet freely, the bar magnet always lies in a north-south direction. Why? Because our Earth is also it also acts as a magnet. So the north pole of the magnet attracted by the south pole, and the south pole of the magnet attracted by the earth's north pole. Therefore, when you are going to place or when you are going to left a free bar magnet, it always lies in a north south direction. It is another one property of the magnet. When we left a bar magnet freely, it lies always in north south direction. North and south direction. So when you are going to place when you are going to place a magnet freely, it always lies in a north south direction. And under one property here, when you are going to consider two magnets, the same poles of the magnets are always repel each other. Same poles of magnet always repel each other, and opposite poles of magnet always attract each other. So when you are going to take two magnets, if you are going to contact two magnets with the same poles, it always repels, it always pulls. So that is repels, that is the same poles of the magnet always repel each other. If you are going to contact the opposite poles of a magnet, they are always attract each other. So these are all the properties of the magnets here. So in your examination there may be 2 or 3 marks question should be asked on this. Write the properties of the magnet, isn't it? So when you are going to consider the magnet, these are all the most important properties of the magnet. Now I am considered that in this chapter, magnetic effect of electric current, they are going to explain the effect of the electric current as a magnet here, isn't it? So one thing I am considering here, this is the compass. This compass contains a needle. That needle, it is also made up of a magnet here. When this needle come in contact with the magnet, what happens here? See, I am showing you. So see here, when this needle come in contact with a magnet, what happens? It has some deflections, isn't it? See carefully here, it shows some deflection. So if you are going to consider any material, if it is a magnet, then it shows only these properties, it should be shows, then only we are going to call it as a magnet. But when we are going to consider this compass, this is also made up of a magnet. When this compass come in contact with one magnet, what happens here? You are going to clearly see here, the magnet, this compass shows lot of the deflections here. Why it is going to shows lot of deflections? Because this magnetic field lines will act on the another one magnet which is present in the compass, isn't it? But when we are going to place this compass towards any current carrying conductor, then also it shows some of the deflections. So it shows deflections only when it is get contact with another one magnetic field lines, isn't it? But when we are going to place this compass with the current carrying conductor, if I am considering this is a conductor, a current carrying conductor, if you are going to place this compass towards the current carrying conductor, then also it shows the deflections. Why it is shows deflections? What means it is? So it shows that the current carrying conductor also has the sum of the magnetic field lines, isn't it? That is nothing but the magnetic effect of the electric current. That was first will be studied by the one of the great scientists, that is S.C. Worstad. So he was the first scientist which he was going to establish, or he was going to explain the magnetic effect of the electric current. So he make an rule how the current carrying conductor or the current carrying conductor acts as a magnet, or what is the effect of the magnetic effect of the electric current, how it shows the magnetic property, or a current carrying conductor how it shows the magnetic property. That will be studied and that will be explained by the one of the great scientists, that is H.C. Worstad. He explains the current carrying conductor and the properties of the current carrying conductor. See here, by one law that is called it as a right thumb rule. That is, current carrying conductor magnetic field due to electric current carrying conductor. When you are going to place this compass towards the current carrying conductor, it shows some of the deflections. Then what it possesses, what it says that electric current carrying conductor has a sum of the magnetic field. So when it has a sum of the magnetic field, then definitely it should have the properties of the magnets here. What are the properties? How they are going to explain? So that will be explained by the H.C. Worstad by the right hand thumb rule. What he explains, right hand thumb rule, when you are going to hold a electric current carrying conductor in right hand, so your thumb indicates the direction of the current, and the other fingers indicate the magnetic field lines, the direction of the magnetic field lines around the current carrying conductor. Is it clear? So when you are going to hold a current carrying conductor, that your thumb indicates the direction of the current, and other finger says the direction of the magnetic field. So magnetic field due to the current carrying conductor, right hand. H.C. Worstad was a first scientist who first explains the magnetic effect of electric current. A magnetic effect of electric current. According to him, what are the properties of the current carrying conductor which shows the magnetic effect? So when you are holding a current carrying conductor, in your right hand, the thumb indicates the direction of the current, the direction of the current, and all the other fingers indicates the direction of the magnetic field. Other finger indicates the direction of magnetic field, around the conductor. So the deflection of the compass, when you are going to place that compass towards the current carrying conductor, it shows that the current carrying conductor must have a magnetic field around it. So according to H.C. Worcester right hand thumb rule, what he explains, when you are going to hold a current carrying conductor in a right hand, the thumb indicates the direction of the current and the other fingers indicates the direction of the magnetic field. So when the current carrying conductor, it has a magnetic field, so it has some properties here. According to him, the magnetic field of a current carrying conductor is directly proportional to strength of the conductor, that is the magnetic field. So the magnetic field of a current carrying conductor, the magnetic field or a magnetic strength of a current carrying conductor is directly proportional to the strength of the conductor. It means if the strength of the conductor increases, then the magnetic field around the conductor, that is also increases. The area of the magnetic field around the conductor, that is also increases due to the increase in the strength of the conductor. And under one property, magnetic field of a current carrying conductor inversely proportional to the distance from the conductor. So another one property of the another one property of a magnetic field of a current carrying conductor, that is nothing but magnetic field of a current carrying conductor inversely proportional to the distance from the conductor. What it means? Inversely means as we go away from the conductor, the magnetic field is also decreases. The strength of the magnetic field is also decreases. That is, magnetic field of a current carrying conductor inversely proportional to the distance from the conductor. As we move away from the, if we are going to consider this is the conductor, as we move away from this conductor, the magnetic field which is around this conductor, that will be decreases. The magnetic strength will be decreases. And according to the strength of the conductor, if you are going to increase, that is first property says the magnetic field of a current carrying conductor directly proportional to the strength of the conductor. As we increases the strength of the conductor, it always increases the magnetic field, that is the strength of the magnetic field of a conductor. And magnetic field of a current carrying conductor inversely proportional to the distance from a conductor. If we go away from a conductor, the magnetic field is decreases. If we go closer to the conductor, the magnetic field increases. That is the another one property of a magnetic field of a conductor, current carrying conductor. So when we are going to consider a straight line, so it says when we are going to conductor a straight conductor or a straight current carrying conductor, the magnetic fields are always around in a straight carrying conductor like this. If you are going to consider this is a conductor, the magnetic field lines around a conductor in this way. When you are going to consider a magnetic current carrying conductor in a coiled way or a coiled structure, I am considering the conductor in a straight line, or it is a straight current carrying conductor. If we are going to consider a coil, that is the current carrying conductor in a coiled shape, then what is the shape of the magnetic field lines around the coiled current carrying conductor? That we'll see now. Magnetic field around a circular coil. So we see how the magnetic field is present in a straight current carrying conductor at any point of the conductor. If we are going to consider this is a conductor, it conducts the current, it has the current flowing on it. So the current carrying conductor at any point, the magnetic field is just like this. It has, so according to the thumb rule, the right hand thumb rule, the thumb indicates the direction of the current and the other fingers indicates the magnetic field lines or the magnetic field around the conductor. If we are going to consider it is in a straight line current carrying conductor, if we are going to consider a circular current carrying coil, what happens here? What is the structure of the magnetic field lines here? At any point when you are going to consider the magnetic field lines here, these are like the circular. So as they go away from the conductor, that becomes a straight lines. Like this. If you are going to consider here, the magnetic field lines are like this in a circular path. As they move away from the conductor, they looks like a straight line. See here. In a magnetic field, in a current carrying conductor in a circular coil, the field lines are also in a circular structure. So in this case also the magnetic field lines are also in the form of circles, but as we move away from the conductor, these magnetic field lines are look like straight lines. They are become straight lines. As we move away from a conductor, in a circular coil, as we move away from a conductor in a circular coil, the field lines, magnetic field lines becomes straight lines. What happens here? At every point, at every instant of a magnetic current carrying conductor, it should have a magnetic field. So as we move away from the conductor, these field lines becomes a stator. That will be looks like a straight lines. That will becomes a straight lines. At every point you are going to see here. At every point, as we move away from the conductor, these magnetic field lines are becomes straighter here. That is the field lines. How we are going to see how the field lines are becomes there in a current carrying conductor, which is in the form of a coil. If we are going to consider these coils in a number of which I am considering here only one coil. If the number of coils are present, what happens here? That is nothing but a solenoid. Magnetic field lines in the solenoid, or a magnetic field in a solenoid. Magnetic field in a solenoid. Magnetic field in a solenoid. What is a solenoid? What is a solenoid first? Solenoid is a number of coils, insulated copper coils arranged in a cylindrical manner. The number of copper coils arranged in a cylindrical manner, that is called it as a solenoid. Number of insulated copper coils arranged in a cylindrical shape. That is known as solenoid. What is solenoid? The number of insulated copper coils. I am considering only here one coil, one electrical conductor, that it is in the shape of the coil. But when we are going to consider number of coils, the insulated copper coils arranged in the cylindrical manner, that is known as the solenoid. So what is the case of the magnetic field here? When we are going to pass the electric currents through the solenoid, what happens? What are the characteristics of the magnetic field here? What happens here? That will be seen now. If you are going to consider this is a solenoid, so as we know already, electric current carrying conductor, that is it has some magnetic field, and it acts as a magnet. So what is the field lines in an electric current carrying solenoid? If we are going to pass electricity through the solenoid, how the field lines are going to be structured here? Due to the coiling of the electric current, all the field lines around the magnetic field, these are the field lines. So these are the magnetic field lines. When you are going to consider the field lines in the solenoid, what happens here? These are very similar to the field lines of the bar magnet. The field lines of the bar magnets, as we studied already, how the field lines are present in a bar magnet. Outside the magnet, the field line starts with the north end and ends with the south pole, isn't it? And inside the magnet, The magnetic field lines starts with the south pole and ends in the north pole. See here. So the magnetic field lines inside the solenoid is also same as a bar magnet. It acts as a similar to the bar magnets. And what is the use of the solenoid here? It is used to make that is the some of the iron like thin low iron like materials into the magnet. That magnet, it is called it as an electric magnet. To make the magnet, so to make the electric magnet, we are going to place that smooth iron rod into the solenoid, and when we are going to pass the electricity due to the magnetic field, that smooth iron will be get converted into a magnet. To make the electric magnet, we use the solenoid here. So the electric field lines, the magnetic field lines inside the solenoid are similar to the field lines of the bar magnet here. So one question arises here in the experiment which we are going to see. When a compass will comes towards a magnet, it will be, what happens in that case? It somewhat what here? So it shows somewhat deflection. That shows it applies some force on the magnet which is present in the compass, isn't it? So when you are going to place this compass towards the current carrying conductor, in that case also it shows some of the deflections. So it shows some of the deflections, then it shows that will be applies the magnet, that the current carrying conductor applies some force on this compass, isn't it? That shows that current carrying conductor applies some force on it. So how it going to be applies that some force? What is the force here? How the force will comes? That will be studied by the one experiment by the Flemings here. So the force due to the magnetic field by a current carrying conductor, that will be explained by the so that one of the scientists, that is called it as Andre Flemings, that is the one of the most important the scientist who explains. Andre Murray Ampere, the scientist who explained first the force exerted by the magnetic field due to the current carrying conductor with his experiment. He considered one stand here. What he did, see here, he considered one stand he attached one rod with it, and he take one aluminium rod, and he coiled a wire around it. And he connected the one end of this wire. To the battery. The positive side of the battery. So Andre Murray was the first scientist who explains force exerted by a magnetic field line of a current carrying conductor. So he made an experiment to explain how the magnet will apply the force on a current carrying conductor. That will be that he make a setup. He take an aluminium rod and he coiled the current carrying conductor around the aluminium rod, and he connected the coil towards one end of the coil towards the positive end of the battery, and one end of the coil towards negative end of the battery, and he placed that rod inside the horseshoe magnet. You have to remember, he placed that bar inside the horseshoe magnet. So what happens here? When the current is not flowed through the conductor, so it is not acts on a magnet, then there is no deflection here. But when he switch on the current, the current carrying conductors, it acts as a magnet. It has some of the magnetic field lines here. When the current flows through the conductor, due to the magnetic force, it will be pulled at the left side. So it will be pulled, that rod will be pulled at the left side away from this magnet. It pull away from this magnet due to the magnetic force which will comes in a current carrying conductor. And when he was going to change the direction of the current, he changed the direction of the current by making the adjustment in the connections. Then only that rod will be pulled right side. So from this experiment he comes to know that due to the change in the direction, the magnetic force applied by the magnetic field, it also changes. He comes to know that the magnetic force applied by the magnetic field, that also changes with the direction of the current. And he explains that that will be explained by the Fleming's left hand rule. How the force will be changes, how the force will be acted, that will be explained by the Fleming's left hand rule. Now we shall study what is that Fleming's left hand rule. Fleming's left hand rule. So according to the Fleming's left hand rule, you have to arrange your left hand 3 fingers in a such a way that they are mutually perpendicular to each other, like that. They are mutually perpendicular to each other. According to left hand rule, what it represents, you have to arrange the 3 fingers of the left hand in a such a way that they are mutually perpendicular. So the first finger indicates the direction of the magnetic field, and the second finger indicates the direction of the current, and the thumb indicates the direction of the force. In which direction we get the force, that will be explained by the Fleming's left hand rule. According to left hand rule, what it states, arrange your left hand first 3 fingers in such a way that they are mutually perpendicular. They are mutually perpendicular to each other. See, why he considered the mutual perpendicular? Why? Because he observed that the moment of the bar is more when the magnetic field, it will be perpendicular to the other magnetic field. When the magnetic field of the conductor is perpendicular to the magnetic field of the Harshov magnet, then only he get the more displacement of the rod. Therefore he consider here, when the magnetic field, it is the magnetic field of a current carrying conductor that is perpendicular to the magnetic field of another magnet, then only we get the more displacement. Therefore he consider the direction of the magnetic field and the current carrying, the direction of the current will be perpendicular. We should be keep that the directions of the magnetic field and the directions of the electric current in the perpendicular, then only we get more of deflection, that is more moment here. So therefore he explains the left hand rule, that is we have to place the first 3 fingers of the left hand in mutual perpendicular way. In the left hand, the first finger indicates the magnetic field, and the second finger indicates the direction of the current, and the third finger indicates the moment, the force, the direction of the force. If the magnetic field, it is in the direction, if the current is in this direction, then the force will be in this direction. That it shows the force applied, the force exerted by the magnetic field each other. So that is such a way that they are mutually perpendicular to each other. The first finger indicates the direction of the magnetic field, and second finger or a middle finger, indicates the direction of the electric current, and thumb indicates the direction of the force. So, according to Fleming's left hand rule, the forefinger indicates the direction of the magnetic field, the middle finger indicates the direction of the current, and the thumb indicates the direction of the force. So, the Fleming's left hand rule will be utilized for the most of the materials to prepare most of the material. That is one of the material which will be making with the help of the left hand rule, that is nothing but the electric motor. This electric motor, it is very usable in nowadays. We can see the electric motor in every electrical equipments which we are going to see. For example, electric motor, it is used in the mills, the electric motor that is used in the fridges, the electric motor it is used in the some of the toys, isn't it? So electric motor it is used in the fans, isn't it? So that electric motor, it is prepared on the basis of the Fleming's left hand rule. So this is all about how the electromagnet that will exert the force. So how the current carrying conductor or the magnetic field of the current carrying conductor exerts a force, isn't it? So that will be studied in this session. In next session we are going to continue how it works, the electric motor, what are the parts of the electric motor, how it will be constructed and how it will be worked. And also in the next session we are going to study the Fleming's right hand rule, that is nothing but the generator rule, what are the factors of the right hand rule and what are the factors of the electric generator, that will be studied in the next session. Thank you.